Okay. So I go. So hello everyone to this first lecture. So my lectures in general will be about partition identities, but on this first lecture I will give more of an introduction to partitions in general, which will be useful for my lecture, but also for the 4 other lectures. And so I will start, of course, with defining partitions, because they are the main objects we are studying. And I'm going to split this blackboard into 2 pieces, because I will make the parallel with some other combinatorial objects that we will see. So the definition of a partition is quite simple. So a partition of a positive integer n is simply a non-increasing sequence of positive integers whose sum is n. And these integers in the sequence, they are called the parts of the partitions. So, yeah, so called parts. Okay, so let's start with an example. We can take n equals to 4. So how can we write 4 as a sum of other positive integers? You can do something very simple and by just writing 4, or you can write 3 plus 1, or you can write 2 plus 2, or 2 plus 1 plus 1, or also you can put a partition with only ones. I'll move this a little bit. Oops. Yeah, I'm cheating. Okay, so yeah, so here you have 5 partitions of 4. Okay. So you notice probably that we have chosen a condition that the parts need to be in non-increasing order. So for example, 3 plus 1 is a partition, but 1 plus 3 isn't, with this definition. So actually it's just a convention that we chose, because with partitions we actually don't want to care about the order of the parts, so we just decide on a convention. And it's more or less equivalent to saying that 3 plus 1 and 1 plus 3 are the same partition. But there is another combinatorial object related to partitions, which is called compositions, in which actually the order matters. So let me define that now. So a composition of a positive integer n is this time just a sequence, not necessarily non-increasing, of positive integers whose sum is n again. So let's take the same example, n equals 4 again. So we'll see that there would be more possibilities, of course. So for the number 4, we cannot exchange any order. We just have one possibility, it's still 4. But as mentioned previously, so 3 plus 1, this one will correspond to 2 different compositions, which were 3 plus 1 and 1 plus 3. Then for 2 plus 2, even if we exchange the numbers, it's still the same. Then for the one with a 2 and 2 ones, we have 3 possibilities. So we have 2 plus 1 plus 1, 1 plus 2 plus 1, and 1 plus 1 plus 2. And again, the partition with all ones, it doesn't change if we change the order. So that's also just one composition. Okay, and in total we have 1, 2, 3, 4, 5, 6, 7, 8. 8 compositions of 4. Okay, so So now that our objects are well defined, we will see that actually there is a nice graphical combinatorial representation for them. So let's start with partitions. And here the graphical representation is called either Ferrer's diagrams or Young diagrams. And it is quite simple, as you will see now on an example, which will be self-explanatory. Can someone give me a partition? Yes?
5 plus 4 plus 1.
Thank you very much. That's a very nice example. So if we take 5 plus 4 plus 1, then the Ferrer's diagram of this partition will simply be a diagram where you put 5 boxes on the first line and you align everything through, like on this column here. So here you put 4 boxes and you put 1 box at the end. So you simply draw several rows, with as many boxes as the corresponding part. Okay. For compositions, there is also a graphical representation. Actually, there could even be several of them. You could also do the same thing with compositions. But I'm going to show you one that will be useful to find the formula for the number of compositions of n. So let's do this. So this time I'm going to do something maybe a bit more general, because it will be also useful later. So you write, so here I will write, so compositions. If you want to represent a composition of n into k parts, you can draw some dots like this, and oops, so you will have n dots, and you can simply put some bars in the spaces between the dots to make some separations. So let's say I put a dot here and a dot there. So here on this example we would have, here it would be k equals 3. So we put 1 less bar than there are of parts. And the composition here would be 2 plus 1 plus n minus 3 on that example, assuming I didn't put any bars in there, in the dots. Okay, so those two representations are quite different. And actually, there is another difference between those two objects. It's that for compositions, it's quite easy, and I will do it in a minute, to give an exact formula for the number of compositions of n into k parts. But on the contrary, it's very difficult to find an exact formula for the number of partitions of n, or the number of partitions of n with some added conditions. And there exists one that has been proved using the circle method that Walter will mention in his lectures, but it's really not useful in practice, and it's like a terribly big formula that would fill the whole blackboard, so I'm not going to use it. So here we could write that there is no simple. Of course, simple depends on the taste, but I think almost anyone would agree that this one isn't. So no simple exact formula. And here we will see right now how we do that. So to compute an exact formula here for the number of compositions of n into k parts, you just use the graphical representation that I showed. And here I put n boxes. So how many spaces are there between those boxes? Does someone want to participate? N minus 1, thank you very much. Yes, so there are n minus 1 possible spaces for putting the bars, and we want to put k minus 1 bars in some of them. So that means that there are n minus 1 choose k minus 1 compositions of n into k parts. Okay. So this is the type of combinatorial formula that one is used to in basic combinatorics, but yeah, it doesn't exist here. However, for partitions, even though we cannot derive a simple exact formula, we can still study them quite well by using a tool which I will now introduce and which is called generating functions. And you will also see just a bit after that actually generating functions of partitions are quite easy and convenient to compute. So this will make up for the small problem which I just mentioned. Okay, so I'm going to define generating functions now. Okay, so I'm going to do definition again. So we consider some set A, a set of combinatorial objects So you can think of partitions because we're in this school, but you can also think of anything else, like graphs, trees, even composition. I mean, yeah, any object that you want, as long as it's a combinatorial object and therefore has a size associated to it. So we call little a of n the number of partitions of not partitions of combinatorial objects. I'm too much in this in this topic, I guess. Of combinatorial objects. Yeah, objects of A with size n. Okay, and the generating function for A and sometimes for generating function, I will later write GF for short. So it's defined as, I will write A of Q, but with a straight letter, and this will be the sum for all non-negative n of A of n, Q to the n. Okay. So actually there are many advantages to generating functions, because if you're able to compute the generating function, and if you want a particular value, if you give me some particular n, let's say, I don't know, 1,000,000, and I want to compute a of the value you gave me, so a of 1,000,000, I can take the generating function and, for example, use a computer or do it by hand and extract the coefficient of q to that particular n, and that will give me the answer. However, it's not exactly the same thing as having a general combinatorial formula, as I just said. It didn't exist for partition. So, but still, you can do a lot of things. Also, if you're able to show that two generating functions are equal, then by equating the coefficients of q to the n on both sides, you can show that for all n, the coefficients are equal. So these tools are very useful in combinatorics. And they also satisfy a couple of convenient properties that I will now mention. So let's consider two sets. So let's say we will take them disjoint to not have any problems. Sets, so again, of some combinatorial objects. And with an and bn, their respective number of elements. Of size n. Then, and again, and yeah, a of q and b of q, their respective generating functions. Then, actually, you can do two very simple operations with generating functions. If you consider a of q plus b of q then this is the generating function for the disjoint union A union B, is the generating function for A union disjoint union B. And you can also find a nice interpretation for the product of two generating functions. So A of Q times B of Q is the generating function for the product A times B, so for pairs of elements where the first one is in A and the second one is in B. Okay, and yeah, and also I will write what I just said. Yeah, maybe that's another property. Like if if A of Q, actually it's an equivalence. So A of Q equals B of Q. If and only if A of n equals B of n for all n. So that's what I was just saying by equating the coefficients of Q to the n on both sides. Okay, so with all this, we should be able to study our partitions in a convincing way. So we want to compute the generating function for partitions. But before doing that, I will start with a toy example, which is simpler and which I think gives most of the ideas. So let's assume I'm just going to compute a product of three terms like that. 1 plus q, 1 plus q squared, 1 plus q to the third. So far it's just a product, and I will expand it. So let's do that, but maybe in a slightly unconventional way, as you will see. So I start with the terms where we only pick one. Then for those where we pick two, I will, instead of writing q to the 3 for q times q squared, I will write 1 plus 2, but you may see some connection with partitions appearing already. So we have 1 plus 2, 1 plus 3, and 2 plus 3, and I'm missing one where you pick all the powers of q, so you have q to the 1 plus 2 plus 3. Okay, so if you look carefully at the exponents of q on here, you can see that actually you have exactly once each of the partitions that can be formed by using the parts 1, 2, and 3, and where the parts are distinct. So that can give you a beginning of idea of how things will work. Now let's look at the left-hand side. So here we can interpret this as a slightly unconventional way maybe to define partitions, not exactly the same as here, but we could say that a partition into distinct parts, which can only be equal to 1, 2, or 3, is actually a triple ABC, where each of the ABCs are either empty or 1 for the first element. Maybe I will write on top, empty, that's not empty, that's a Q, empty or 2 for B, and empty or 3 for C. And that way you can, by doing all the possible combinations, you get all the possible partitions that you can get by using those 3 numbers. Okay, so now we said by using the rules here that if you have disjoint union, so that's the same as having the choice between 2 elements if you want, then the generating function will be the sum of the generating function of each of the 2 sets. So let's imagine the first set is just a set containing the empty partition, and I didn't want to erase, and the second one is just the singleton equal to 1. So for this first element, you have the disjoint union of those 2 very simple sets. And the empty partition is generated by 1, because we take the convention that it's of size 0, and the partition with just one part equal to 1 is simply generated by q. So this is the generating function for the first term of this triple. For the second, we do the same. Either we don't take anything which is generated by 1, or we take the number 2, which is generated by Q squared. Same for 3. And so far we have the separate elements, but why do we have a product here? Well, that's because of the second rule here, because we're actually here considering a triple, so it's a, yeah, here I said it only for pairs, but I mean, of course you can iterate this rule if you want. So here you independently choose the first element, then the second one, then the third one. So it's actually like taking the product of sets, and so you take the product of generating functions as well. So here we just showed that this is exactly the generating function for partitions into distinct parts equal to 1, 2, or 3. So now we can apply this in more generality to compute first the generating function for partitions into distinct parts. Okay, so let's do this. You will see it's really the same idea. So we will call d of n the number of partitions into distinct parts. And we consider the generating function. So d of q, this will be defined just like we said here. So it's the sum over all non-negative integers of d of n, q to the n. And actually, we can really apply the same principle as we just said. So here, we were only allowing the parts to be 1, 2, or 3. But actually, you can do exactly the same reasoning over all the possible integers. So for each integer k, you will choose whether k does not appear in the partition, which would correspond to a 1, or if it appears in the partition, which would correspond to k. Okay, so, and again, you can see it as a, well, this time it will be an infinite list, but of elements which are either empty or the number that you pick, the number k. Okay, so it's really the same principle, except you go up to infinity here, instead of stopping at 3. And actually, you can also, if you want, add some other variables in your generating functions. So here I gave the formal definition for univariate generating functions, but actually you can have several variables. So for example, if we consider, I will keep the same letter, d of nk, to be the number of partitions, well, actually, maybe I just take another color, it will be simpler and faster. Some red, okay. And I will not use this one. Okay, so let's say instead of just d of n, we consider d of nk to be the number of partitions of, well, I had forgotten to say of n, so it's actually good that I'm going back on this sentence. Yeah, sorry, so of n into, now k distinct parts, we want to count the number of parts. So actually, you can also do a generating function like that, and this time it will have two variables, so I will call the second variable z. And so here we will have d of nk, and we will have two exponents, so you have q to the n and z to the k. And all the rules I mentioned are still true. It's also still true that if two generating functions are equal, the corresponding coefficients are equal. So this is all the same as yesterday. So now, where do I add a z here? Actually, it will just be here in front of the q. Because when we pick the 1 here, that means it was just an empty part. We don't pick the number, so you don't add any part to the partition. But here, when you do the product and you pick the z to the q, that means that q appears as a part. So it adds 1 to the number of parts, so that's why we multiply by z to the 1, but of course you don't write the exponent 1. Okay, so that's how it appears. And actually there is a more concise way to write this by using a symbol that you will see a lot in this school, so called the Küppershammer symbol. So I'm gonna do a little place here where I define it. So Küppershammer symbol. So it's defined as AQ sub n, and it's the product for k equals 0 to n minus 1. The 1 is a bit touching the y, of 1 minus AQ to the k. And n is either an integer or infinity. And if it's infinity, then you have an infinite product, just like here, for example. And also, you can, if you want, you can write sometimes when you have many Küppershammers, it's simpler to write them in a sequence if you want. So let's say A1, comma, etc., comma, AM, Q sub n. That's simply the product of A1Q sub n times A2Q sub n, etc., up to AMQ sub n. Okay, so that's the notation. And therefore, we can rewrite this in a simpler way. We can say, yeah, this is just minus ZQ Q sub infinity. Okay, so this is, oops, sorry for the noise. So this is a generating function for partitions into distinct parts, and now we're going to see how we can apply similar ideas, but with slightly more, with one more difficulty if you want, to actually compute the generating function for partitions, where the number of parts isn't restricted. Okay, so now let's call, I'm going to do it directly with the variable z here, so let's call P of nk the number of partitions of n. I'm going to split here too into k parts. And we will do again the generating function. So P of nk, q to the n, z to the k. Yeah, well, yeah, I think I did some, I forgot to add something in red, even though it's, you probably have corrected that yourselves, but yeah, I also need to, of course, sum over k, otherwise it's not correct. Sorry about that.
The next product, is that k starting from 0 or starting from 1?
Oh, 1, yeah, you're right, sorry. Yes, indeed. Yeah, thank you very much. Yeah, so yeah, here also it was starting at 1, so yeah, I made a mistake, yes. Yeah, because the parts, they can only be positive integers. We don't consider zeros, otherwise we would have infinitely many partitions because you could add as many zeros as you want at the end. So yeah, so they should start at 1. Okay, so now you consider the same principle as before, except that now for each positive integer k, you will decide whether it appears not at all, or once, or twice, or 3 times, etc., etc. So, actually now, you have, and I will take some other letter, so let's say L. We have the product for all L positive integers of 1 if the part L does not appear, or ZQL if the part appears once, or Z squared Q to the 2L if it appears twice. So we have a Z squared because that creates 2 new parts, etc., for all possible powers here. So I think you might have noticed or recognized here a geometric series. So there is a simpler writing for that. So that would be 1 over 1 minus ZQ. And we can also write this using the Küppershammer symbol that we just defined. So that would be 1 over ZQ Q sub infinity. Yes?
Is it ZQ to the L inside the product?
Yes, it is ZQ to the L. Thank you. Yeah, it's getting late, I guess. Yeah, indeed. Yeah, so yeah, I think right now it's correct, but thank you very much. And so yeah, so here you as you saw, those generating functions, they are not too complicated to derive, and they will have many applications. So in my lecture, it will be mostly proving partition identities. We will see in a minute what it is. And in some other lectures, for example, it could be deriving asymptotic formulas or like making the connection with some Q-series identities. So they will have several different applications. And let me also mention one last detail, which is that here we did it for partitions where the parts could be anything. But it's actually almost free with this method to add some congruence conditions on the parts. So I will again take my, maybe I change color again. I can do that in red, green, sorry. So let's now say the parts are congruent to A modulo B, let's say. Why not? And I don't know, I will write P sub AB. And so you will really do the same thing, except that now instead of considering all the positive integers L in our product, you will only multiply over the integers that are congruent to A modulo B, because they are the only ones who are allowed to appear. So, okay, maybe I add this. So L, so here we add the condition that is congruent to A modulo B, and here too. And actually what we would get here in the end would be ZQ to the A, Q to the B sub infinity. Because here in this product you would only have terms of the shape B times J, let's say, plus A, and yeah, that's how you get that. And you can do also the same thing for partitions into distinct parts. So I will go back to that. Okay, so partitions into distinct parts. Yeah, I will also add this AB here. So congruent to A mod B. And it's really the same thing here. So we again take the product only for those integers. And here you would also get some A here in the power and some B here. Okay. And actually I'm not doing this just because it's nice, even though it is nice, but this is because in partition identities, which we will now study, actually often you have congruence conditions that appear. So we will see that right now. So maybe I can start by saying what a partition identity is, and that's important because it will be the main purpose of this lecture. So a partition identity is a theorem that says that for all positive integers n, the number of partitions of n satisfying some conditions and I said that those conditions are often congruence conditions, so I will mention it here. Is equal to the number of partitions of n satisfying some other conditions. Okay, and often, as you will see, especially in Rogers-Ramanujan type identities, which I will mention in the next lectures, these other conditions are often difference conditions between consecutive parts. Okay, so I say often, but that's not, it doesn't need to be the case as long as you have one type of partition and another one, it's an identity, no problem. Okay, so I will now give you the most ancient and also maybe the simplest partition identity of that type with congruence conditions and difference conditions, and it is Euler's theorem. And it is as old as 1748, so quite a long time ago. And it was initially proved using generating functions, and actually Euler invented them, so he put them to good use almost immediately. So this identity is quite simple. It says that for all n, the number of partitions of n into odd parts equals the number of partitions of n into distinct parts. Okay, so let's take some number. I'm gonna try to be a bit original and do n instead of the 4 I did before. So how many partitions of n are there into odd parts? So you can write 5. You can write 3 plus 1 plus 1. And you can also write 1 plus 1 plus 1 plus 1 plus 1. That's longer to say than for 4. And so I think that would be all the partitions into odd parts for 5. So that's 3 partitions with odd parts. And now if we want to consider distinct parts, we can do, again, 5. If it's all alone, of course, it will be distinct from nothing. And you can write 3 plus 2. And you can write 4 plus 1. And those are all the possibilities if you want the part to be distinct. So we also have 3 partitions into distinct parts. Okay. So at least on this example it works, and we will actually show on just this half of the blackboard that actually this is true for all n, and we will give a generating function proof, as I just promised. So for that we should remember something I said before, which is that if 2 generating functions are equal, that also means that for all n, the corresponding number of objects are equal. So actually what we want to show is that those 2 generating functions are equal. So we will start with the generating function for partitions into distinct parts, which we actually computed there. But here we will not take the z into account, because here you see there is no number of parts involved in this theorem, and actually even if we wanted to keep it, it wouldn't work like in any obvious way. So when you have too much information in a multivariate generating function, you can just set the variables you don't need to be equal to 1. And this is what we do. So actually, the generating function for partitions into distinct parts, where we only count the number n that is partitioned, we had done it. And that is just that one. And that was the product for k larger than 1 of 1 plus q to the k. And we want to transform this into the generating function for partitions into odd parts. So we will do an extremely deep trick, as you will see. We multiply by 1 minus q to the k, and we divide by 1 minus q to the k. So we did a lot of things, as you can see. But actually, even though it looks quite simple like that, it will actually prove the theorem. Because on the numerator, you might have some memories from high school or middle school, and remember that this equals 1 minus q to the 2k. And on the denominator, I will actually write it as a separate product to maybe be a bit clearer. We still have the product of 1 minus q to the k. So here, on the denominator, we have the product of all the 1 minus q to any positive integer. And on the numerator, you have the same thing, except you only have the even numbers that appear here in the power of q. So actually, all of these even numbers, they will simplify between the numerator and the denominator. And if you remove all the even numbers from all the integers, you get just the odd numbers. So this is actually what happens, and you end up with 1 over the product for k. I don't know, doesn't matter how I write it, but let's do it like that. So the product over all odd numbers. And yeah, if we want to write this with Q-Poshamers just because we like them, that would be q squared infinity. And from what I said on that blackboard there, if you set z to be equal to 1, actually you might recognize that the little a from there would be 1 and the little b would be 2. So that's exactly the generating function for partitions with parts congruent to 1 modulo 2, so odd parts. So actually, this is sufficient to prove Euler's identity. So quite a simple proof. The other proofs that I will show in my other lectures will be a bit more intricate, but this is always a good start. And I will finish by giving you an idea of a bijection that we could also do for this identity. Because ideally, when you're a combinatorialist, you're happy when you prove an identity, but it only tells you that, that two sets have the same cardinality. But actually, if you want to have the most information possible, you like to know sometimes exactly which element from one set corresponds to which element of the other set. And that's what bijections tell you, because they really give a one-to-one correspondence. So I'm just going to show you the idea. So let's take, let's make a table with partitions into odd parts here and partitions into distinct parts there. And so we'll do the first few numbers. So for the number 1, it's quite simple. You have one partition into odd part, and it's also a partition into distinct parts. So if you want to put them in bijection, I think everyone would guess which matching we should choose, and it's the one. When n equals 2, you have a partition into odd parts, which is 1 plus 1, and a partition into distinct parts, which is 2. And again, the bijection here is also quite obvious. You don't have a choice. But you don't have a choice, but it gives you some information. Because here you see you had something which was into odd parts, but not into distinct parts. You had a part 1 that repeated, and actually you put them together to form a part equal to 2. So let's see if that can also be applied to further cases. So for 3, the partitions into odd parts are either 3 or 1 plus 1 plus 1. And the partitions into distinct parts are either 3 or 2 plus 1. Okay, so this is the first interesting case because we have a choice. But of course you could do either you map 3 to 3 and 1 plus 1 plus 1 to 2 plus 1, or you can do the contrary. Of course you are free. But if you want it to be a bit coherent with what you've done so far, actually here you saw that the part 1, which was both odd and distinct, you just left it alone. So it would make sense to also leave 3 alone and send it to itself. And on the contrary, when you had the part that was repeating, we saw that we were merging them to get a part of double size. So it seems a bit more intuitive to make this choice. And we will see if we can also apply it a bit later for further values. So let's take the number 4. It can either be written 3 plus 1 or 1 plus 1 plus 1 plus 1. Yeah, too many ones. So into distinct parts, yeah, here you can have either 4 or, well, 3 plus 1 also. Okay. So if we still want to stay a bit in the same style of rules, well, 3 plus 1 is already distinct, so okay, why? Let's not touch it and just send it to itself. And in 1 plus 1 plus 1 plus 1, I don't know. Then many repetitions occur, so many that I don't know how many ones I read. So actually, that would make more sense that this one is the one that's transformed to something new, so to the 4 here. And actually, here I just did the first numbers, but you can do a general process like that. You can look at your partitions into odd parts, and you want to turn them into partitions into distinct parts. So if they are already distinct, you're all happy, you don't do anything, you just send them to themselves. And if there is a number that is repeating, so here it's only once, but it can be something bigger if you have bigger numbers. Actually, so if there are 2 consecutive numbers that are equal, you merge them together into a part of double size. And you repeat this process until you have only distinct parts. So actually here, it wasn't just one step with the algorithm I described. It was actually a bit more. So let's look at this one. We read it, we see 1 plus 1. Oh, well, that's repeating. So we're going to set this 1 plus 1 to be equal to 2 instead. And yeah, so far we continue. You read this again, you see 2 plus 1, well, so far no problem. Plus 1, oh, repetition. Okay, so that's not so good. So here we send that to 2 plus 2, because we transform this 1 plus 1 into a 2. And we read this number again, 2 plus 2, well, repeating again. So we merge them together, and we get 4, and 4 is okay, because it's a partition into distinct parts. And this process will always terminate, because you can, well, you decrease the size of the partition every time, so worst case, in the end, you end just with 1 part, but it will always be distinct if you have just 1 part, so you end up with something distinct. And the reverse bijection is also relatively simple. You take a partition into distinct parts. If they are odd, you're happy, you leave them as they are. And if there is an even part, you split it into 2 parts of half the size. And again, you repeat this process until everything is odd, sorry. And again, worst case, you obtain something with only ones, but then this one is always into odd parts and you cannot split it more. So like, it also terminates in that way. And yeah, so that's the bijection of Euler's theorem. And there exists some generalization of it to where you can, instead of considering things modulo 2, there is a version modulo k, but we won't go into this detail now. And I think I will stop here, and thank you for your attention.